Welcome to another short video on engineering studies. I'm just going to go through the concept of bending moments and shear force diagrams. So what I'm doing here is I'm giving you a starting situation where we've got a basic beam bridge which has got two forces of 60 and 30 newtons on that beam, and there's gaps of 2 meters each on this beam. And what we're going to be doing is we're ultimately wanting to see if pretend this blue tack, this piece of blue tack that I've got here is a beam. When we load a beam with forces, we're wanting to see basically what happens to that beam as we load it. So if in this example we'd have 60 newtons and 30 newtons, and so a beam would probably be loaded or have a pushing or bending that looked something a bit like that at the end of the day. But this gets quite complicated as you change and increase the complexity of the loading. So what we're wanting to do is saying, given a flat beam and given the basic forces, how does this beam look once it's loaded, and where does it bend the most? So in this one it's quite obvious it looks something like that because there's more force there than there, but we're going to have a quick look and see how we can calculate that. So the first thing you normally do with these kinds of calculations is that you're just going to draw force lines, and you're going to have to draw them through all your forces. So the starting point, as with all of our calculations, is to go ahead and calculate the reaction forces at A and B, and to do that you do your sum of your moments is equal to 0 around a point B, and start at A and then do your calculations. What I've done is I've already done this, and I've worked out that this is going to be 40 newtons and this will be 50 newtons reaction forces at A and B for this particular setup. If you don't know how to do that, go back and look at the reaction force calculations for bridges and you'll be able to look at how to do that. But now that we have 1, 2, 3 forces for our particular beam, we can go ahead and just draw a vertical rule line down each of the force lines. So a force acts on a line. We're just drawing through these force lines so that we've got basically ruled lines down here, and we're going to do what's called a shear force diagram. And what I'm going to do is create a set of axes. So I'm going to make this my 0 point over here for my shear force diagram. And so what I'm going to effectively do is I'm just going to be taking each of these forces and adding them to my shear force diagram, starting from 0. So from here I'm going to go up 50 newtons. So I'm going to do a scale choose a specific scale. I'm going to choose a scale of possibly 1.5. That'll be too big, so 5 going up. That's my 50 newtons going up, which is this 50 newton force. And then for shear force diagrams, you just draw a straight line across to your next force, and I'm going to do 60 newtons down, so that's going down to -3. So 50 minus 60 would effectively be -10. And then again, I draw my line across. And now 30 newtons down, so that's 1.5. So if you think about it, this would be 10 minus 30 would be at point -40. And then of course of 40 newtons up. So I go across. And of course in a bridge scenario, because we've got two fixed points, because my bridge is coming to two fixed points and there's no bending at the end of those 2 points, I'll end at 0 and I'll start at 0. So it's just a very simple way to make sure you've done the right thing, is that for a bridge that's got two fixed points, they should always start and end at 0. For an aeroplane wing, for instance, that's being bent upwards because of thrust, so you've got a nice wing, the tip of the wing is bending upwards, so your shear force diagram might not end at 0, but it would start at 0. So that's my shear force diagram, which is showing all the shearing forces within my bridge. And if you look at this, you can label these areas above and below the 0 as 3 separate areas. 1, 2, 3. If I want to colour those in, it might help you see that's the first area, that's the second area, and that's the third area. And the reason that's important is because when we do this for a bending moment diagram, which I'm going to bending moment diagram, we need to add up these areas. So in this diagram, I was adding up the different forces. So I went 50 across, and then from here I went down by 60, which took me to minus 10, cross, down another 30, and then cross, and then up the 40. I'm going to do the same thing with my bending moment diagram. I'm going to draw another set of axes, and I'm going to give it started at a label of 0. But this time, because it's a moment, and what is a moment? A moment is a force multiplied by a perpendicular distance, just as a reminder. What we're going to do is we're going to multiply the force by its distance. So the distance in this case is 2, 2, and 2 meters. So this force multiplied by its distance is 5 times 2. So we started off over here at a distance of 0, and by the time we get to this distance of 2 meters, 50 times 2 is, and I'm going to do another scale, let's do 2. So let's do 2 centimeters equals 100 Newton meters. So I'm just putting a dot over here to say this is 100 Newton meters, meaning this area over here represents 100 Newton meters of bending moment. Now I need to look at my second area. This is 10, because it's only 10 down. I'm just looking at the box area here. 10 times 2, what's the area of that? 10 times 2 is 20, but it's negative, don't forget, it's below the line. So I add that area to that area. So 100 minus 20 is 80. So it's a bit of a small scale, but I'll put 80 over there, Newton meters. So now I've got 100 Newton meters and 80 Newton meters over there. And then finally, my last one is minus 40 times its 2, which is this area over here. So 40 times 2 is 80, so 80 minus 80, and it should go back to 0 because this is a bridge that's supported and fixed at both corners. Now I'll draw these lines up. And what you should see is you should see an exact opposite or invert of what we said the bridge was going to look like. We said the bridge is going to look like something like this. It's going to bend something like that. And what you see is it's an exact replica or invert of that. So the bridge was going to be bending like that, and when your bending moment's done, it should look exactly upside down, or if you turned it upside down, that's what the bridge should look like when it's bending in a bending moment diagram. So very simply, that's all you need to do. You just need to draw your lines down, put in your shear force diagram with your forces on those force lines, sum the areas, and this is where people make mistakes. You don't add them separately. You've got to add the negative area to that positive area and this negative area to that positive area, and just graph them, and then join the lines, and you should be left with a bending moment. And notice, importantly, that this point of 100 Newton is the maximum bending moment for this bridge, i.e. where the bridge bends the most. And that number, or that unit value there, is important for bending stress calculations. So you'd probably use that in your bending stress calculation, which we'll do a different video on. Hopefully you'll find this helpful.